Hello, everybody. We're going to start chapter 3, section 1, which is now finding volumes using cross sections. Because remember what we found last time in last chapter, we found areas. This time we're now going to look at volumes, which are areas. Well, area is base times height, which is 2-dimension. Volumes are areas times some width, or base times height times width. Base times height times width. And that's W. So it's 3-dimensional figures. Okay, so that's what we're looking at this time. What we're going to do this is we use three methods I want to look at is by using cross sections. In other words, if we had a graph, make it a 3-dimension graph because we have 3 dimensions, and it was of any blob, any picture. So let's say there's some blob. What we're going to do here is we're going to take and slice this with a sheet. And where that sheet intersects the blob, we'll have the imprint of that area. So that's what we're doing. It's cross sections of a solid in a, this is a plane, this is a solid. So we're looking at this intersection where the plane and the solid intersect. And then with all those different planes, we add them up, and that gives us the volume of the entire object. We'll look at all three methods of finding the volume of a solid. The first method is the method of slicing, like we just did up here. We're just going to take our solid, whatever it is, and just slice it with these planes. And each of these planes will have a certain width. And as those widths go to 0, we have individual microscopic slices. Then we'll look at what's called the disk method. And lastly, the washer method. All right, so we talked a little bit about the first one. So the first one, we have the slicing. We use a plane and cut, or actually slice the solid and we use a plane, slice it, and slice the solid with perpendicular slices. Right, so that's what we're going to look at. And also remember, so if we had an object here, we can find the area because it's only 2 dimensions, base times height. And now in this case, we have depth. So this is going to be the volume. That's what we're looking for. So let me define, which you'll see a lot, is this word. You'll see the word cylindrical solid all over the place. And it's pretty much as I said, it doesn't have to be a circle, just has to be a smooth shape. It could be circular, it could be square, it could be regular, it could be anything. All right. So let's look at this. Let's look at how we're going to derive our formulas. Yes. No. Yeah, they have a whole bunch of colleges that are visiting and they have up and down the hallway. So if I get distracted again, sorry. So we're looking for the volume. Volume of a solid. Remember, because we have that, I'll use a cylinder. And I use the plane and I'll cut that plane with the solid. I have a small, because this solid, this plane has a depth. It has a width and it has a height. So it has a volume. So if we add up all those volumes, then we'll get, looking at from the side, here's our cylinder. We're gonna slice, 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 and add up the width, the volume of all these slices. All right. What is volume made up of? The volume is made up of the area of this part here, the area of that circle part there, at some value. So here's some value x. That slice will have this area imprinted on it. So it's the area at that x value. And the slice will have some width. That's delta x. So that's what we're looking at, that slice to get that area. So the volume is made up of the area times the width of that. All right, so remember, we want delta x. We want delta x to go to 0. right? So in other words, we have to increase the number of n's. So n, this top number of slices, has to go to infinity. Because if it goes to infinity, then these slices get a lot smaller. So our formula becomes, well, using the Riemann sum formula, we get the volume equals the limit as our n's go to infinity, the summation of I equals 1 to n of ax sub I delta x sub I. So we're looking for that. And also remember that the Riemann sum formula found us the area. So it's the integral. So this is our formula that we'll be using. All right, let's look. And typically our procedure, because now we have one more step involved, and solving volumes of solids equations. The first step of the picture, so you know what you have, what you're looking for. Find the formula for your A of x, your area. The area of the cross-section part. It's you cut that with that plane, it's whatever's inside there, that's the area we're looking for. From the graph, find the bounds of integration. Or what domain you're on. And integrate A of x. Now, the reason this works is area is a two-dimensional object. When we integrate an area, we get the volume, which is a cubic function. So areas are square, volumes are cubic. Okay, our first example. Example 1. A pyramid 3 meters high has a square base. That is 3 meters on a side. So it's 3 meters square. The cross section of the pyramid perpendicular to the altitude x meters down from its vertex. So the point is a square x meters on the side. Find the volume of the pyramid. So a pyramid that's 3 meters high has a square base that is 3 meters on a side. The cross section of the pyramid perpendicular to the altitude m meters down from the vertex is a square. Okay, so let's draw a picture first. Yeah, it has to be 3 dimensions because it's a pyramid. So we know it starts at the vertex is there. And the last one is way back there. So if we cut this on the out, there's our plate. This is cutting through at X right there. So we know it's 3 meters here, 3 meters there, 3 meters there, 3 meters there. This is going to be all X's since we don't know what that is. And it crosses the at 3. Okay. So since this is a square base, that means this is a square part. So the area of this part is the base times height. X times X is X squared. It goes from 0 to 3. So we look at our integral. So we have the integral from 0 to 3 of our area, 0 to 3, x squared dx. So we integrate that, we get x2 plus 1 over 2 plus 1. So it's x cubed over 3 from 0 to 3. Three cubed over 3 minus 0 cubed over 3. That one's 0. So that's 3 times 3 times 3. So it's 3 times 3 is 9 meters times meters is meter squared. Oh, no, it's 3 of them. So that's our volume. Pretty straightforward. That's because we had a square base and it's all straight lines. The rectangular base would have been a bit more difficult, but we would have gotten through the whole thing. Example 2. A curved wedge is cut from a circular cylinder of radius 3 by 2 plates. One plane, I'll call it P1, is perpendicular to the axis of the cylinder. The second plane, which I'll call P2, crosses the first. P1 at a 45-degree angle. At the center of the cylinder. Find the volume of the wedge. So a curved wedge. Let's draw a picture. Consuming my X and my Z. Okay, so the curved wedge and then it also goes up. It's a wedge. All right, so what does it tell us now? What cut from a circular cylinder base? Okay, so there's a cylinder base. Curved wedges cut out, kind of like when they chop down trees. So it's radius of 3. So this is 3, and that's -3. That's 3. It's circular cylinder by 2 planes. So the first plane cut down this way and cut it in half this way. And the second one at a 45-degree angle. So that angle there is 45 degrees. So let's figure out the formula, the area. The formula we'll be using, since this is circular, is x squared, since that's center, x squared plus y squared equals radius. X squared plus y squared, we know the radius is 3. Okay. Okay. Now, we cut a sliver out of here. The height's going to be x. So base times height. So the height is x. And the cylinder, let's solve for y. Get y squared equals 9 minus x squared. Okay, so that's the base. Oh, okay, so we said one plane perpendicular to the axis of the cylinder, which is across this way, so it chops it down that way. So we have half a cylinder. Second one cuts at a 45-degree angle through the center of the cylinder. Okay, so that equals that. 9, so we have x times square root of 9 minus x squared. So that would just be that part. This would just be the circle part, the base. And the height. So this one would go from 3 or x to the function. And we have two of those. We have one on this side and one on this side. Yeah, because we're going to do our integration from 0 to 3, and we have to go from 0 to -3. We're not going to go from -3 to 3. Because it's an even function, I could double it. Yeah. So the volume equals from 0 to 3, I got 2x radical 9 minus x squared dx. So if we integrate this, so okay, we could say that u is equal to 9 minus x squared. Du would be negative 2x. Yeah, the derivative of that. So we need a negative. Yeah, so we have integral of 0 to 3 of u to the power 1/2. There's that there. Square root of u du, which is du dx. That's okay. Which makes it u to the power 1/2 du, u to the 1/2 plus 1, 1/2 plus 1 from 0 to 3. So it's u to the 3/2 over 3/2. Flip the bottom. U to the 3/2 from 0 to 3. Ooh, I've got that negative. So it's still negative. Okay. Negative 2/3 times u. U is 9 minus x squared to the 3/2. I'll put that in front and just work this out. So we get 9 minus 3 cubed squared, or 3 squared, to 3 halves, minus 9 minus 0. 9 minus 9 is 0. Negative 9 to the power 3 halves, which is equal to negative 2/3. Square root of 9 is 3 cubed. Negative makes it positive. 2/3 times 27 is 9. 9. 9 times 2 is 18. It's not difficult, it's just long. All right, let's look at example 5. So example 5 states Cavaliere's principle says that solids with equal altitudes and identical cross-sectional areas at each height have the same volume. The solids with equal altitudes and identical cross-sectional areas at each height have the same volume. Duh, yes. This follows from the definition of volume. By definition, the cross-sectional area A of x and the interval AB are the same for both solids. Yeah, it kind of goes like a no duh. That was Cavaliere's principle. An Italian mathematician from the 1800s or 1900s. Next section. I mean, part of this one. Solids of revolution. The disk method. So this method is simply a solid or a plane that's being rotated about a specific axis. So to find the volume of a solid, like this, hold it, my pen's dying. Gotta find me another pen. Hold it. Right, that one's dead. So to find the volume of a solid like this, we first look at the cross section area. A of x. Since we're going to use this method, we have to notice that the area of a disk of radius r where the radius is the distance from the axis of revolution. The one we're going to flip it over. To the planes region, the boundary of the plane that we're looking at. So to find the volume of the solid like this, we first look at the cross-sectional area A and notice that the area of this disk radius r, where r is the distance from that to the axis of revolution, we talk about r. So this is the distance from the area there. The A of x is pi r squared, or pi radius, since it's a function of x, because it moves. This gives us the definition of the volume by disks rotated about the x-axis. Because we're using x, we're rotating about the x-axis. So the volume is from A to B, the area dx, which is area is pi r of x squared dx. So that's the disk method. It's example 4. The region between the curve y equals square root of x, with x being between 0 and 4, and the x-axis is revolved about the x-axis to generate a solid of revolution. And the volume. Okay, so it says the region between the curve y equals square root of x, the bound 0 to 4, and the x-axis. So let's draw a picture first. It's y equals square root of x from 0 to 4. So what this looks like is, well, the square root of x looks like that. And since we're rotated about the x-axis, it'll be that picture. And we put the slice in the middle somewhere. The distance up and down is r of x, which is from the x to the y, that's the square root of x. The function itself is square root of x. All right, so let's put it all together. The volume equals a to b of pi r of x squared dx. A is 0 to 4. Pi r is square root of x squared. Square root of x squared becomes x. The pi is a constant. It can go out. Right, so the integral of x is x1 plus 1 x squared over 2 4. Which becomes 4 squared over 2 minus 0 squared over 2. Is 8 pi. That's pretty straightforward. Let's look at number 6 or number 5. The circle. Rotated about the x-axis. To generate a sphere. Find the volume. It's radius A. But it's a sphere. That means if we look at it from the side, from a 3-dimension, it's a sphere. Okay, so what do we know? We know the radius is y. Which is square root of a squared minus x squared. We have to get the functions with respect to x and y. So the area part that's the radius. So we have a squared minus x squared, because that's squared already. All right, so the volume goes from negative A to positive A of the area. This formula, a squared minus x squared. I, the integral of this one with respect to x, integral of ax, a squared is a squared x, 2 plus 1 over 2 plus 1, negative a to a. A squared x minus x cubed over 3, negative a to a. So it's a squared times a minus a cubed over 3 minus a squared times negative a minus negative a cubed over 3. So it's a cubed minus a cubed over 3, negative a cubed, positive a cubed over 3. We get a cubed minus a cubed over 3 minus negative a plus minus negative a cubed plus a cubed over 3. A cubed minus a cubed over 3. Distribute. Plus a cubed minus a cubed over 3. A cubed is 2a cubed minus 2a cubed over 3. By 3 over 3. So it's 6a cubed over 3 minus 2a cubed over 3 equals 4 pi a cubed over 3. Okay, let's look at example number 6. Find the volume of the solid generated revolving region bounded by y equals radical x and the lines y equals 1, x equals 4, about the line y equals 1. Okay, let's look at a picture of this. So square root of x about the line y equals 1, so I'm up to 1, so that's my new x-axis. Rotated. So from this line to x equals 4, there's the curve. With that line there, and x equals 4. So the ending is at 4. So my bound is going to be from 0 to 4. My R is going to be, since I'm rotating it about y equals 1, I'm shifting it up. So it's radical x minus 1 squared. So 0, 4 pi rx squared. No, it's going to be squared because this is the function that's going to be squared here. Let's put all these pieces together now. Not 0, because it goes from x equals 1. Yeah. Because where it intersects when x equals 1. So I'm only looking for this outer shell. Rotate it about. So I start from 1 and go to 4. Pi square root of x minus 1 squared I can't do this one, so we have radical x minus 1, radical x minus 1. X minus radical x minus radical x plus 1. So x minus 2 radical x plus 1 dx. Integrate each of those. X squared over 2 so it's 1/2 plus 1, 1/2 plus 1. X squared over 2 is 2 3/2 x to the 3/2 plus x. Okay, now I'm ready to plug in the values. Four squared over 2. 4 to the power 3/2 minus 1 squared over 2. Okay. Four squared 16 divided by 2 is 8. Square root of 4 is 2 to the power 3 is 8 plus 4. One squared is 1, so it's 1/2. 1 squared root of 1, so it's minus 4/3 plus 1. Eight plus 4 is 12. 32 over 3. One half plus 2 over 2 is 3 over 2. Not 33. 12, 32 over 3. 3 over 2, that is 1 over 2 plus 2 over 2 is 3 over 2. 3 over 2 minus 4/3. So a common denominator here. Same thing here. $36 minus 3 minus 32 over 3. 9 over 6 minus 8 over 6. $36 minus 32 over 6 minus 9 minus 8 over 6. 4 over 6 and 1 over 3. Four over 3, 2 over 2. 8 minus 1 is 7 over 6 pi. Wow. That was pretty painful. Okay, let's look at number 7. That was 3 pages worth. Example 7. Find the volume of the solid generated by revolving the region between the y-axis and the curve x equals 2y, where y is from 1 to 4, about the y-axis. Let's see what this graph would look like. And so x is equal to 2y. It's the same if it was y over 2x. Your radius is 2. The domain is from 1, or ranges from 1 to 4. So if I plug in 1 there, it's got 2. So I have to start off at 1. It's going to be 2. So from there, that's the base. Because it's rotating about the y-axis. And the graph itself looks like this. It's the Atari. But it goes to, that's 1, 2, 3, 4. So it stops there at 4. It goes from 1 to 4. And that's my radius. It's a function with respect to y because it's 2 over y. And the domain is from 1 to 4. All right, so the volume equals 1 to 4 ry squared dy. All right, so let's see what we have here. So it's 2 over y squared dy. What is that? So I took out the pi, went from 1 to 4. Distribute, that's 2, so it's 4 over y squared dy. or y to the power -2. Four comes out, so it's 4 pi. -2 plus 1, -2 plus 1 equals 4 pi from 1 to 4. Y -1 over -1. -1 over y. Negative come out in front. One over y, 1 to 4. One over 4 minus 1 over 1. This is 4 over 4, which makes it -3/4. Negatives cancel. The 4's cancel, so it's 3 pi. That wasn't so bad. Number 8. Find the volume of the solid generated by revolving the region between the parabola x equals y squared plus 1 and the line x equals 3, x equals 3, about the line x equals 3. All right, so find the volume of the solid generated by revolving the region between the parabola so the parabola of this one. Instead of going up, it's going to be this way. And plus 1. Now, since that is with the y, that means it's a horizontal shift, 1 unit. So we're looking at that graph up to 3. So from 1 to 3. Okay, and we revolve it about the line x equals 3. So it'll be a mirror image over there. So our graph starts at 1 because it's shifted over. 2, 3. So we have to go the other direction. So now when x is 3, we have 2 square root of 2. So our height is square root of 2 at 3. Which means we have to have a negative square root of 2 down here. at 2 is square root of 1 is just 1. So football. Since we're now our function with respect to y, we're looking at any value y here. We're gonna look at finding that area there, that region. So that R is the function with respect to y. About the line. So, okay, so then from there to there, that's the radius of the circle. So that's 3 minus the function itself, which is y squared plus 1. Two minus y squared. That's my R. All right, so now I'm ready for my equation. My volume equals, since you're going vertically, remember these are going from positive to negative. So negative square root of 2 to square root of 2. Pi r of y squared dy. The integral of square root of 2 to square root of 2. Take the pi out. Is 2 minus y squared squared. Foil this out. I got 4 minus 2y squared plus y to the 4th. Again, for this one, you gotta do 2 minus y squared times 2 minus y squared and foil them out. Well, I can do each one of these. So I have 4y minus, add 1 to the top and divide by that number. 5 over 5. Makes it pi 4 square root of 2 minus 2 square root of 2 cubed over 3 square root of 2 to the 5th over 5 minus 4 times negative square root of 2 minus 2 over 3 negative square root of 2 cubed to the 5th over 5. So it's pi 4 square root of 2. So now square root of 2 cubed is square root of 2 squared times square root of 2, which is equal to 2 square root of 2. Same thing here. Square root of 2 to the 5th is squared, squared, 2. So it's 2 times 2, square root of 2 over 5. That's the first part. Negative 4 radical 2. So it's negative 2 radical 2. Negative 2 times square root 2 over 5. Four square root of 2. 4 square root of 2 over 3. 4 square root of 2 over 5. Negative 4 square root of 2. Negative and negative makes it a positive. 2 times 2 is 4. Square root of 2 over 3. Minus 4 square root of 2 over 5. Four root 2 distribute that. That becomes a plus. Oh, no, that becomes a minus. No, no. This becomes a plus 4 root 2 minus 4 root 2 over 3 plus 4 root 2 over 5. Four plus 4 is 8 square root of 2. Negative 4, so it's negative 8 square root of 2 over 3. 8 square root of 2 over 5. So 15 ZLCD. 15 times 50. 120 root 2 over 15. So it's 40 root 2 over 15. 24 root 2 over 15. Some of these are pretty big. 15. It's going to have root 2. And it's 80 plus 20 is 104. That number is wrong. Plus minus plus. Put the negative ones in there. It's negative 4 radical 2, so it becomes a positive. And minus ooh, that's where I messed up. That should be a 4 because 2, 2, so we have 4 minus 4y plus y squared. That's where it is. So we just change all these. So this should be at 8. So it should be a 16. 16 times 5 is 80. 120 minus 80 is 40, so it's 64. The answer is 64 pi radical 2 over 15. Yes. Okay, so that was the disk method. Let's do some examples now with the washer method. The third section, the solids of revolution. The washer method. So when does this occur? If the region revolve to generate a solid, if this region does not border on or cross the axis of revolution, the solid has a hole in it. So the solids generated are washers. In other words, if our graph doesn't, if we're going to rotate it about the x-axis and it's not touching it or crossing it, then there's that hole open there. So it's the low end here is the high end. So that's why I call it the washer method. Because we only want this area here. And when we revolve it around, it becomes a sphere with a hole in it. A donut, not a donut, but actually a ball. All right. So the dimensions of the washers are represented this way. The outer one is the large R. And then little r is the inner. Bound. So that one's they're going to be Rx. Right. So we have to give two different names because we're using two different specific values. So let's look here. Areas of washers. The area of a washer, pi times the radius x squared, minus, that's the outer, minus the inner. So it's r of x squared minus r of x squared. This is the washer method. All right, so let's look at a couple of examples. Example 9. The region bounded by the curve y equals x squared plus 1, and the line y equals negative x plus 3 is revolved what is that? Is revolved about the x axis. To generate a solid. Find the volume of the solid. All right, let's look at the picture. All right, so we have so what we have here. We have y equals x squared plus 1. So x squared is a parabola, plus 1 means it's lifted up. It's lifted up. And the line negative x plus 3. So that's 1, 2, 3. This and when it's solid around the x-axis, so it has to be perpendicular. So that's going to be our height. So let's see what we have here. We have a point here at 1, 2. We have another point here, so let's see where the two functions are equal. X squared plus 1 equals negative x plus 3. X squared plus x minus 2. So it's x plus 2, x minus 1. So we have an intercept at negative 2, and we have an intercept at 1. So if we plug in negative of negative 2 plus 3, we get 5. So we have a point at negative 2, 5. The curve down here is x squared plus 1. This line is y equals negative x plus 3. So the distance between those two that's the highest point. So whatever x we start off with, that's the distance. Yeah, we have to rotate it about the x-axis. So down here, we'll have the same looking thing. We're going to forget what r is. What is the radius going to be? We have r minus r. So negative x plus 3 minus x squared minus 1. No, then that'll be a parabola, so it can't be that. So we're going to use this as our radius, because that's the high point. It's capital R. So it's negative x plus 3. Because it's R. And little r is x squared plus 1, because it's the lower one. All right, so let's put this stuff together. We have the volume equals from A to B r squared x minus r squared x dx. So we go from, our bounds are from -2 to 1. Look at the x values. So it's -2 to 1. So we have r, big R is -x plus 3 squared, minus little r is r squared plus 1 squared dx. So this first one is going to give us negative times negative is a positive x squared, -3, -3 is -6x plus 9. X squared is x to the 4th plus 2x squared plus 1. -2 to 1. X squared minus 6x plus 9 minus x to the 4th plus 2x squared minus 1. So it's x squared plus minus 6x. Six x plus 9. X to the 4th minus 2x plus 1. So I -2 to 1, x squared minus 6x plus 9 minus x 4th, 2x squared minus 1. Minus x to the 4th goes to the 4th. That's plus, which then becomes a minus. So x squared minus 2x squared is minus x squared minus 6x plus 8. Minus x to the 5th over 5, x to the 3rd over 3, x squared over 2, 8x. Negative 1/3, no, 1/5, minus 1/3, minus 3 plus 8. Two to the 5th over 5 plus 2 to the 3rd over 8 minus 3 2 squared minus 16. So negative 1/5 minus 1/3 plus 5. Two to the 5th. 32 over 5. 8 over 8. 8 over 3rd. What am I doing? 4 makes it negative 12 minus 16. Negative 32. That's negative 33 over 5. Negative 9 over 3. 17 plus 16. So that becomes 3. So we have negative 33 over 5 plus 15 minus. Yeah, that's minus. This is a minus. So that becomes a plus. So it's 31 over 5. Hmm. Plus 3 plus 8 makes it positive 5. Over 5. 9 over 3 is 3. Plus 5 is 8, 20, 36. 36 times 5 is 30. Okay. Oh, it's the constants. Okay, let me start from this point. Okay. Negative x to the fourth minus x squared minus 6x plus 8 dx. Negative x to the fifth over 5, negative x to the third over 3, negative 6x squared over 2, 8x, negative x to the fifth over 5, x minus x to the third, 3x squared plus 8x. So it's negative 1 over 5 minus 1 over 3 minus 3 plus 8. So negative 5 was negative 3, so it's a positive 32 over 5. 2, 4, 8. It's a positive 8 over 3 minus 12 minus 16. Distribute. Negative 32 over 5, negative 8 over 3, positive 28. Negative 33 over 5, negative 9 over 3, plus 33. Negative 33 over 5. Negative minus, that makes a positive 30 over 1. So it's 117 pi over 5. Page. Okay. And we have one more example. Example 10. The region bounded by the parabola y equals x squared and the line y equals 2x in the first quadrant is revolved about the y-axis to generate a solid. Find the volume of the solid. Y equals x squared. And the line 2y. So it's up 2 over 1. So this is 1 up 2 over 1. So it's this line. So x squared equals 2x. So at x equals 0 and x equals 2. That's my domain. But now since I'm going with respect to y, I gotta find out where the y values are. So this one here is 0, 0. That's my lower bound. And when x is 2, 2 times 2 is 4. So they cross at 2, 4. So the bounds of integration are going to be from 0 or from 0 to 4. And so that's going to be our thingy. This is the radius I need. So the outer one is square root of x. And the inner one is 2x. Okay. So our equation is going to be r big R minus little r. This is my v. So it's from 0 to 4. So it's going to be square root of x squared minus 2x squared will be 2 minus 4x squared. Oh, nope. Well, because we have y equals 2x and y equals square root of x. Since we're rotating about the it's y equals x squared. So we have to solve for x. So x is equal to y over 2. And then x is equal to square root of y. So this inner one will be y over 2, and the outer one will be square root of x, or square root of y. So we have the square root of y and y over 2, which is equal to y squares that minus y squared over 4. So it's y squared over 2 minus y cubed over 3 times that 4. Four squared over 2 minus 4 cubed over 12 minus 0. The pi goes out in front. Sixteen divided by 2 minus 64 divided by 12. So that could be divided by 4. 4 was in there 16 times. 4 was in there 3. So it's 24 minus 16 over 3. Makes it 8/3 pi. Yeah, I forgot because we're rotating about the y-axis. So we have to make all of mine with respect to dy. Because we're rotating about the y-axis. So all the functions have to be with respect to y. All right, sorry it took so long, everybody, but that's 3.1. Have a good weekend.